Well, we're having a look at parametric equations of circles, ellipses and hyperbolae in this session. That's a very interesting subject, so let's get started and see if we can make some great headway. Well, first up we've got a circle is defined by the parametric equations x equals 2 plus 3 cos theta and y equals 1 plus 3 sine theta for theta going from 0 to 2 pi inclusive. We have to find the corresponding Cartesian equation of the circle and state the domain and range of this relation. Now, I should explain before we get into all this stuff that basically with parametric form we have both x and y. They're basically expressed in terms of a third variable which we call a parameter. Okay, that's how it works. They're both dependent upon this third variable called the parameter. Okay, that's how it works. Now, having said that, let's just make some headway and see how this works out. We've got x is 2 plus 3 cos theta, y is 1 plus 3 sine theta. Now, NB, you've got to know this. When you have one of these expressed in terms of cos and the other one expressed in terms of sine, we've got ourselves either a circle or an ellipse. If the coefficients are the same here in front of the trigonometric term, you've got a circle. If they're not the same, you've got an ellipse. That puts it in a nutshell for you, okay? So when the coefficients of the trigonometric terms sine and cos are equal, we have a circle. When the coefficients of the trigonometric terms sine and cos are different, we have an ellipse. Now, this is a circle. This is a circle, okay? Always you have to have one of them a cos and one of them a sine. It doesn't matter which one's which. X can be sine or y can be cos. They can also be plus or minus here as well. All that really affects is basically where they start and which direction they're moving round in the trajectory around the curve that they form, which in this case will be a circle. And you can have a great deal of fun changing these to pluses and minuses and basically altering the direction and all kinds of interesting things. By changing this to sine and this to cos, you change where they start off from as well, and all kinds of good stuff. But we'll just go with this one that we've got here as defined, and we'll work out the Cartesian equation. When you work out the Cartesian equation, you lose all information about where it started, what direction it's going in. All you see is the snail trail of where it's been. Okay, that's what you get, right? So this is a circle. From equation 1 we know that cos theta, we make cos theta the subject of equation 1, we make sine theta the subject of equation 2, and we use this marvellous theorem that cos squared plus sine squared equals 1, and we sub for sine theta and cos theta from these above equations here into this expression here. And what do we get? We get that, and it looks very, very much like a circle. It is, and it's basically a circle where the centre is 2 and x is 2, y is 1, and the radius is 3. Okay, for you and me, and basically now that's not the end of the story. We've got theta going from 0 to 2 pi, okay? Theta goes from 0 to 2 pi, hence both x and y would complete one full period each. Okay, that means, see this, look, if theta goes from 0 to 2 pi, then cos is going to go through one full cycle, and so is sine. Okay, now let's have a look at that. This here, let's just flesh this out a bit. This is x, this is basically x is 2 plus 3 cos theta. Now, on the vertical axis here, I've got x. On the horizontal axis, I've got theta. Right, now this is really important because x is expressed in terms of theta, and so over here, as we'll see in a moment, y is expressed in terms of theta. So we have to look. So this vertical axis will show us the x values for a full cycle of theta. So therefore the domain in terms of a Cartesian equation, which we got over on the previous screen, will be all the x values possible, which are derived from working out the trajectory the vertical axis variables for this trajectory here where theta is moving along the horizontal. So yeah, I'll show you in a minute. I'm getting a bit tongue-tied. See, that's it. That's it. That is the x. The x moves from -1 up to +5. Okay? Remember, look, it's 2 plus 3 cos theta. Cos theta moves from -1 to +1, so therefore 3 cos theta will move from -3 to +3. Okay, so it's 2 minus 3 up to 2 plus 3. In other words, -1 up to 5. That's it. That's better. So that is going to be the domain, right? That is going to be the domain. Yes. Now, similarly with the y variable here, that's also expressed as 1 plus 3 sine theta, e.g. in terms of theta, the third variable, the parameter. And if we examine what y does, that's what it does, right? Sine theta goes from -1 to +1, therefore 3 sine theta will go from -3 to +3, and therefore 1 minus 3 is -2, 1 plus 3 is 4, and we've got it. We've got it. So therefore y goes from -2 to +4. Okay, so the domain is -1 to 5, that's the x. The range is from -2 to 4. Okay, that's it. Right, yes, I know it's a bit different, but you know, these things are really great fun. But as I say, when you move into Cartesian form, you lose all information about where the thing started, if there was a starting point, such as from theta is 0 to theta is 2 pi, might be the restricted domain of theta. Then you can work out where the thing started, which direction it went in, all kinds of stuff. And all that information is lost when you go into straight Cartesian form, if that's all you've got to work with. Yeah? This example here. Find the Cartesian equation of the curve with parametric equations. X is 3 plus 3 sine t and y is 2 minus 2 cos t, where t could be any real number. Okay, well that's any real number, and we have to describe the graph. Okay, now, as I've written here, when the coefficients of these trigonometric terms sine and cos are different as they are here, this one's got a coefficient of 3, this one here's got a coefficient of -2, but 2 is the number, the magnitude. Therefore, that is definitely an ellipse, because you have to have one of them in terms of sine, one of them in terms of cos, so that qualifies in that respect. And because the coefficients of the trig terms, the sine and cos terms, are different, this is an ellipse. Okay? So, yes, it's an ellipse. Let's write our equations out. There's x, there's y. Okay, now we're going to do the same thing as we did in the previous example. We're going to make sine t and cos t the subject, and we're going to plug those into this expression here, that sine squared t plus cos squared t has to equal 1. We're going to sub for sine t and cos t from the above, and we're going to get that. Alright, now, just simplifying that a little bit, we get that. That is an ellipse, that is an ellipse. Okay, and the centre is 3 and 2. The x semi-axis is 3, and the y semi-axis is 2, and here comes the ellipse, right? There's the centre point there, and there's the axis intercepts, yes, and this, there, I'm just showing you very clearly that these are the semi-axis. That's the x semi-axis, right, is 3 units long, and the y semi-axis is 2 units long, so indeed it is an ellipse. It's a squashed circle. It's an egg. Yes? Nice, isn't it? Yeah. But do you see, if you've just got that graph there, that's the Cartesian graph, you've got no clue, if you're just working with that equation there, which is this equation over here, anything about the trajectory itself. You just don't know. All you've got is x versus y. Nothing that was time dependent forming the graph is known at all. Yeah? Alright, now, what's this one? This is example 33 for you and me. We've got, find the, oh, this is a very interesting one. You're going to like this one. These are different beasties. Find the Cartesian equation of the curve with the parametric equation. This time, x is 3 sec t, and y is 4 tan t. Now, these are different. When you have sec and tan, guys, you don't have a circle or an ellipse, you in fact have a hyperbola. You've got to know that. Can you please remember that from now on? If you have secs and tans, they're it is a hyperbola, okay? It is a hyperbola. And depending on which one's plus and which one's minus, it can be a left and right branch hyperbola, or it can be an up and down branch hyperbola. That's really what determines that, okay? Now, in addition, in this question, we've got a restricted domain. So this is very, very fascinating. When they do that, usually they're going to make it only one branch or one part of the hyperbola. So you've got to be very, very careful to analyse what this restricted domain means, right? If it's T is any element of R, no problem, it's the whole thing. But if it's restricted like this, you better watch out, because they're setting you up for a booby trap, okay? If you're not careful. Now, as I've said here, parametric equations where x and y are sec and tan functions of a third parameter. In this case, it was T, or vice versa. Tan and sec, in other words, we're dealing with hyperbolae, right? So we've got x is 3 sec t and y is 4 tan t. Now we do exactly the same thing as what we did before. We make sec and tan this time the subject, like that. And then what we do then is we don't use sine and cos squared equals 1, we use this one. Sine squared plus cos squared equals 1. We use 1 plus tan squared t equals sec squared t. And we plug these things into this one, and watch what happens. Yes, we sub for sec t and tan t from the above, and we get that. We get that. Okay, now if we reorganise that a little bit, we're going to get that, which is a left and right branch hyperbola, if ever I saw one, because it's left and right branch, because the positive pronumeral squared term is the one that gets the intercept, so that you would get x-intercepts in this case, so therefore it must be a left and right branch instead of an up and down branch hyperbola. So it is a hyperbola, centre at the origin, yes, and for the asymptotes, now we have to work all this out as well, because we have to find the Cartesian equation, and finding the asymptotes is part of doing that. So the asymptotes, with the asymptotes you neglect this 1. You just neglect that, because if you don't have a 1 there, and if you have a 0 there instead of a 1, you are going to get the equations of the asymptotes if you solve it for y in terms of x. So from that, you would do that, and that's what you would get. You get y equals plus or minus 4 over 3x, yeah? Now, this is the very interesting bit, guys. This is the interesting bit. T going from pi on 2 to 3 pi on 2 is in fact a restricted domain, as I was explaining before. So let's just analyse what that means, okay? So we need to examine both x and y over the domain of the restricted domain of the parameter t. So therefore we've got x equals 3 sec t, where t is that restricted domain, and we've also got y as 4 tan t to spell it out very clearly. Same restricted domain. Yes? Now, let's go over the screen and have a look at the exciting way that this all pans out. Now, what have I got there? Well, I've got x equals 3 sec t. That's the graph of 3 sec t between x is pi on 2. Well, I'm using x here on the calculator, but we really mean t, right? This would be t is pi on 2. This is t is 3 pi on 2, and that red bit there, sandwiched in between them, is 3 sec t within that restricted domain. Now, what I'm trying to get at here, guys, is that, yeah, that's the restricted domain showed to you very clearly, but what are the values of x which will apply to that domain? Okay, that's minus 3 there. That's minus 3, and so obviously we're going to get minus infinity up to and including minus 3. Yes, so that's what x can range from. Okay, from minus infinity up to and including minus 3. Do you see how important it is to work this out? I'll show you in a minute. Now, this one over here is y equals 4 tan t. Now, there's that's the, even though these show as x on the calculator, I really mean t. So that's from pi on 2 to 3 pi on 2. So there's my restricted domain. That should read t. Just a moment, I'll fix it. There, that's better. I've got that fixed now. Okay. So now we're going to look at what values y can take, which are corresponding to that restricted domain of t. Well, you can see, well, because this is an asymptote here, It's basically y is going to go from minus infinity to plus infinity, or all real values, right? Now, let's see how this pans out on the graph of the hyperbola, the Cartesian graph of the hyperbola, which we got the equation of on the previous screen. Have a look. It's amazing. So we know from the Cartesian function that x can go, because of we've been finding out from this, okay? Yes, because x is a function of t, y is a function of t. They both have their own separate graphs to worry about. We've worked out what x can range from. We've worked out what y can range from. So therefore x goes from minus infinity up to and including minus 3. So let's have a look at that. That's what we're talking about. Everything from here backwards, right? So look, which branch of the hyperbola is getting left out in the cold here? This guy is not in the running. This guy is, right? And y is all real numbers, which means that's what we're saying. So the whole of this branch is allowable, and the whole of this branch, because of what x is doing, is out of the running. So right? So we have the left-hand branch only, so watch how I'm going to rub out the right-hand branch. There's the left-hand branch, and the right-hand branch, goodbye, see you later, better luck next time. Yeah? That's what you've got to do. Now look, guys, if they restrict the domain of the second tan ones, please don't fall into the trap. It's always going to be a restricted domain, which will give you some section of the hyperbola. Maybe one branch, maybe only half of one branch. You just have to basically make sure that you're doing it correctly by doing this kind of analysis that I did up here, right? And don't rush it, otherwise you might mess it up. Yeah, and we don't want to do that. Okay, example 34 now. This says we've got to give parametric equations for each of the following. Now, this means we're going backwards now. We're going back from Cartesian back to parametric. Now, this is pretty interesting because whilst you go from parametric to Cartesian, you'll only get one Cartesian possibility, but it doesn't work the other way. If there are many solutions to these equations, many parametric, in fact there's an infinite number of them, which could all give you the same Cartesian snail trail, if you like, right? Just the x and the y on the one graph. But because you lose all the information about the trajectory, how it formed, where it started from, which direction it basically rotated around in or formed, when you go from, when you end up with the end result here, you lose all that information. Therefore, if we really kind of reconstruct a parametric curve, there's many variants of the parametric trajectory which could also form the same snail trail, is what I'm trying to say. So, yeah, they're not unique. So I'll show you what I mean. Look, if you had x squared plus 9, y squared equals 9, that is a circle, centre at the origin and radius 3, isn't it? So we could have had y is 3 cos t, x is 3 cos t, y is 3 sin t. That would work because you think about it. Therefore, cos t would be x over 3, sin t would be y over 3. Therefore, if you plug those into cos squared plus sin squared equals 1, you're going to get x over 3 all squared plus y over 3 all squared equals 1, which is a circle, radius 3, centre of the origin. Yeah, but you could also have x is this and y is that. That'll get you the same result. That just means that the circle started in a different spot or rotated around in a different direction or something like that. You could also have this, right? Look, as long as you've got a cos t term, a sin t term, and the coefficients are the same, you can play around with this forever. Now, there's another one. There's another one. Now you could even get more fancy, and you could start changing this, what's in here. As long as they're the same, this is a 2t and a 2t, as long as they're the same, you'll still get a circle, okay? That means that the circle is just going to form a bit faster or slower, depending on what's in here, okay? So you can see that, you can just go on forever. Yes, etc. Now, number B, what was number B? Oh, yeah, that's an ellipse. It's got the centre at the origin, and the x semi-axis is 4 and the y semi-axis is 2. Now, we can play around with that one forever too. You could have all kinds of things. You could have x is 4 cos t, y is sine 2t, which if you think about that and work it out, you'll get the idea. Look, cos t is x over 4, sine t is y over 2, so cos squared plus sine squared equals 1, which means x squared over 16 plus y squared over 4 gets you 1, yeah? Or you could do this, for example. Look, I'm changing what's going on in here, and I'm altering the signs out the front. It doesn't matter, as long as one of them is cos and one of them is sine, and you can get that equation there, it works, okay? So again, there's an infinite number of solutions, infinite number. So looking at number C now, that's a hyperbola, just looking at it. It's a left and right branch hyperbola. It's centered at 1 and minus 1. But we've just got to construct our second tan parametric equations from that, right? Now, I might let you pause the video and have a go at that yourself and come back, okay? Right, you back? Okay. Hyperbola centre, 1 and minus 1, it's got the left and right branch hyperbola shape, hasn't it? So we could have had y, now if you think about this, so tan t would be y plus 1 over 2. So that's how you get y plus 1 squared over 4 out of this, if you like. This one, x could be 3 sec t plus 1. Alternatively, you could have had, changing what's going on in here. Changing that t to 3t, changing that t to 3t, etc., etc., etc. Yeah? So, you know, you get an infinite number of solutions. Now, we're going to go over the screen now and we're going to talk about starting points and direction of travel. This is very, very interesting. I need you to understand this because they often ask this in exams. They want to know what was the direction of the trajectory that formed. So we have to go back to parametric again where that information is available to us, because it's not when you're looking at Cartesian form. So let's see. I've got an example for you. We've got x is minus 4 cos t, y is plus 2 sine t, where t goes from 0 to 2 pi. And we've got to find the Cartesian equation, the starting point, and the direction of travel, clockwise or anti-clockwise, yeah? And it's very interesting too. Here's the, we'll do the Cartesian equation. That's nice and easy because we've just been doing that in the last few screens. So we'll go through the old routine again. We say that cos t is minus x over 4, making cos t the subject. We know that sine t is y over 2, making sine t the subject. Cos squared plus sine squared equals 1. Plugging those two equations into that, and what do we get? We get that. That's what we get. Now, just simplifying that a bit. My goodness, a beautiful looking ellipse, isn't it? X semi is, we don't have to worry about all that. We just have to come up with the equation, didn't we? Now, the starting point, coordinate. Now, this is where we've got to get some new concepts happening here, guys. Now, the starting point. You see that t goes from 0 to 2 pi. 0 to 2 pi. So the starting point. Think of t as time, right? So the starting point would be t when t is 0. So therefore we plug that into x and y parametric equations here and here to work out the x and y coordinates, right? So when t is 0, x is going to be minus 4 cos 0. Cos 0 is 1, so x will be minus 4. And y would be 2 sine 0, and sine of 0 is 0, so that'll be 0. So the starting point for this trajectory, which is available from our parametric equations and which is lost when you only have the Cartesian version, is minus 4 and 0. Now, that's 2 out of 3. We've got the Cartesian equation, the starting point, and now we've got to do the direction of travel. Now, this is a very, very fascinating little procedure, guys. This is what you do. For direction of travel, what you do is you basically, the procedure is that we find the position of the particle after 1/4 cycle of the trajectory has been traversed, and then we compare this point to the initial position, which is we've got down here, and it becomes very obvious what the direction of travel has been, and I'll show you. So Yes, it makes it very clear whether you're going clockwise or anti-clockwise. So in this example, when t was 0, we got this point here, minus 4 and 0, didn't we? So now, if we look up here, we know that basically the period of sine t and cos t, they're t inside the brackets here. Cos t, sine t. Now, that means, what is the period of sine t and cos t? What is the period of that function? Well, it's basically 2 pi, isn't it? Yes, so therefore we look for a quarter cycle. That would be a quarter of that, which would be pi on 2. Alright, now we do the same procedure as we just did over here, except plugging in not 0, but pi on 2 to find what x and y would be. So when t is pi on 2, x will be minus 4 cos pi on 2. Now, cos of pi on 2 is 0, so that'll get us 0. Right? Now, also y will be plus 2 times sine pi on 2. Sine pi on 2 is 1, so that'll be, y will be 2. So we're looking at the coordinate point 0 and 2 for me and you when we've completed a quarter of a cycle. Now, come with me, my child, and we'll show you on the graph how marvellous this is. We've just nailed it, guys. There is our graph. There is my starting position. As I worked out on the previous screen, when t was 0, we were at minus 4 and 0. Now, look, there's where we are after a quarter cycle, right? So look, the only way to get from there to there over the course of a quarter cycle, and by the way, we don't use a half a cycle because that would get us over there and we wouldn't know which way we went, either on the up part of it or the down part of it. We'll use a quarter cycle. You get an unambiguous result. So that means, yes, that's when t is pi on 2, and that's the position that we're at after a quarter of a cycle, which means the only way we could have gone from there to there is that away. So, is that a clockwise or is that an anti-clockwise? Of course it's a clockwise motion, isn't it? Yeah? It's a clockwise motion. So, just to finish off, you might like to play around with this now. If you change the sign, the SIGN sign of say the y trajectory to negative instead of positive, what you would in effect do is you would reverse the direction. As the starting point would be the same, you would reverse the direction. It would go around that way. That's what you would get. Now, I want you. That's your homework, to figure out why that would be. And it'll be very exciting homework too. And you can also do all kinds of things to it. You can change the starting positions, you can change the direction, you can do all kinds of marvellous things by the way you manipulate those two parametric equations. And if you take the time to do that and figure it out, you will learn so much in the process that you'll be absolutely unbeatable in this area. Alright, you're a star. Thank you very much, and we'll see you in the next exciting video. Thanks for watching and have a wonderful day.